Hello there and welcome back to Steam It with Steve. Today we're going to go through the next step in our exploration of Boolean algebra. So we're going to cover truth tables. Now truth tables are super interesting. What they do is they give you a map of all the different logic units that you can use. Okay, so if we have inputs A and B, these are all the different combinations that you can do. So you can do 0, 0, 0, 1, 1, 0, 1, 1, or off, 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 on, off, on. And then what we can do is we can map that out. Now this is pretty much all the ones that you would really need to know. So if we do the not of A, we just invert all these numbers. If we do the not of B, we invert all of these guys up here. If we do A, and then this symbol means union, right? Or and, so A and B. So if we look at this, 0 and 0 makes 0, 0 and 1 makes 0, 1 and 0 makes 0, and 1, 1 makes 1. Then this one is the opposite, so this is unioning, right? Which then gives you 0 and 0 gives you 0, 0, 1 gives you 1, 1, 0 gives you 1, 1, 1 gives you 1, and then this one here is exclusive OR. So exclusive OR means that when it's unique, you put a 1, right? So if 1 is occurring just in this once and only once, you make a 1, but if it's anything else, it just is a 0. So it's like OR, except you don't do with the case when both happen. Now, we're going to go through each of these and sort of build up to the last ones up here. And we should see something interesting with this last bit in here particular. So what is a truth table? That's the first question. A truth table is a way of representing a statement's meaning symbolically. Okay, and each compound statement has a single identifying characteristic. So when we use union or and or, they do specific things and they do it in a particular way. Okay. And then this was taken out of a textbook just to give you an example. So if you do your truths and truths, this is what you can do when you fill them in. Okay. And it's just done by practice. The more you practice this, the more you get used to it. And it's super useful, particularly when we're trying to reduce our logic gates down. So the first one we learn is negation. And when we do it this way, what happens is we use a little tilde, which is next to the 1 key on your keyboard. And that just means the not of it. So each claim has a negation or contradictory claim. So for example, if we had the phrase Superman is awesome, the negation to that statement is Superman is not awesome. And that is the exact opposite. So notice that negation doesn't mean Superman is sometimes awesome or it might be awesome. It's very clear that it's the opposite by using the word not. Okay. So for negation in true symbols, we use the tilde symbol, which is found at the top left of your keyboards. So P is equal to Superman is awesome. Not P with the tilde on the front basically means not awesome. Okay, so the truth table that we're going to look at, usually when we merge this together, it's got a whole heap of P, Q's, and R's, which are the inputs. And those are the preferred variables that we'll use to measure the truth of the statement that we're storing in them. Every statement has a possible state, so it's either going to be true or false, on and off. So if we start with P because that's the first one, and I don't know why they started with P and Q and R. Someone can put in the comments, that'd be awesome. But we start with P. If we've got 0 and 1, if we then go not P, right, that then gives you the 1 and then the 0. So negation means the opposite to the truth. Okay, so if P is equal to true, not P will be false. And then similarly, if P is equal to false, not P is then equal to true. Cool. The next one then was you have conjunction statements. Now what happens here is this is where they narrow the options out. Okay, it's exactly the same as the way that we've learnt Boolean algebra when we were talking about and. Okay, so a conjunction statement is a compound claim asserting both simpler claims containing in it. All that means is that it's merging them together to make a new, more complex claim just by using the and statement. So when we use conjunction, we're merging it together, and it's only true if both of the claims are true. So for example, and then we use the little shift and 6, which is the up arrow looking like that. So a conjunction looks something like this. If we do P conjoined with Q, and we do this, so P is equal to Mr. Henderson likes running, and Q is equal to Mr. Henderson likes swimming, P conjoined with Q goes Mr. Henderson likes running and swimming. Okay, so that should be pretty obvious. Just the new terminology that we're saying here is conjunction, which means when we're merging things together. So the conjunction truth table has 2 claims, and each is possible, but we only have the 4 different inputs when we do the 2 to start. So if we have P and Q to go, we just literally do the same as we've been doing all the way before. So if it's P and Q by itself and they're both in the off state, right, when we can join those statements, that would still be false. If we have P and Q with Q being true, that's false. And then if we have P and Q where P is true, that's false. And then the only time when this conjoining is happening is when we do P and Q merge together. So conjunction is only true when both the states are true. Okay, this is the unique case that we talk about. So if you look down here, there is only one time where 1 happens, which is the key case. Now, when you're doing conjunction, it limits your options. So if you've got all these statements, P, Q, R, S, etc., and you did this and this and this and this, the only time that it will ever be true will be that last row, right? Because it's the only time where all of them are true, which makes that true. Cool. The next one that we're going to do is disjunction statements, which is basically an opposite up arrow, which is a down arrow. And then this widens your options. So it means either or both claims containing it are true. Okay. A disjunction is false if only both the claims are false. That's the only time. So there's only one time when a disjunction or an or statement doesn't work. And then that's when everything's set to 0, which is the unique case. So the symbol for disjunction is a down arrow, like we talked about before. And then this is how you would write it. So P disjoined with Q. So Mr. Henderson likes running, and then Mr. Henderson likes swimming. When we do the disjunction with P and Q, Mr. Henderson likes running or swimming. Okay, so that's what the options mean with that. So the truth table for a disjunction looks something like this. Okay, and it's exactly the same that we've done before. So if we have 0 and 0, when we combine those together in disjunction, that's a 0. Now that is the only unique case. Everything else is pretty much going to be a 1, isn't it? So if we have a 0 and 1, there's something true, so therefore overall it becomes true. 1 and 0, something true, so straight away overall it all becomes true. And then 1, 1, straight away everything becomes true. So since this is a disjunction is false only when both the states are false. So if they're all false, this is the key case here. Okay, and I'll fix that typo up there. Sorry, that should say disjunction. So exclusive disjunction is like XOR. And what we do is we use this little symbol here. So it looks like a target, crosshair, sniper kind of thing. And basically it's exactly the same as XOR. So the conjunction is true only if one of the claims is true. Okay. So the symbol for exclusive disjunction is a crosshair. So exclusive disjunction P, exclusive or with Q looks something like that. So Mr. Henderson likes running, Mr. Henderson likes swimming. And then down here we've got Mr. Henderson likes only running or swimming exclusively. Okay, so the truth table for this looks pretty simple. You got P, Q, and then you got P XOR with Q. So 0 and 0 makes a 0, 0 and 1 makes a 1, 1 and 0 makes a 1, and then 1 and 1 makes a 0. So there is no key case or unique case in this case because nothing stands out. Awesome. So hopefully you've picked up on how those patterns work. And now you've got these new symbols that you're aware of how they operate. So we're going to test how you actually go with that. So with this one, I want you just to pause the video, write out these truth tables and see if you can get to the end result. So just pause it there and have a go. Awesome. Welcome back. So we're going to go through with this one first. What you should notice as well, eventually should be at the skill set where someone will give you an expression like this by itself with not M and not Q, not R, sorry, and not F, sorry. So not M and not F merge together, right? And then you will know how to write out all these symbols out here. And it's just the same, we write out our numbers all in order. So if we go from the very beginning with the first one there, that's what it should look like. So we just count as normal. We go 0, 0, 0, 1, 1, 0, 1, 1, and A and F makes 0, 0, 0, 1. That's all you need to do. The next one, so we've got PU, so 0, 0, 0, 1, 1, 0, 1, 1. Not P, we invert all the symbols in here. So the zeros becomes 1, so 0. This then goes 1, 1, 0, 0 because of these. And then we do not P, exclusive or new. So the unique case we're looking for is as long as there's just one in out of the 2 inputs, it becomes a 1. If there's anything else, it's a 0. So even though it's got a 1 and a 1, that's too many 1s because it has to only be 1, 1. So 0 and 1 becomes a 1, 1, 1 becomes a 0, 0, 0 becomes a 0, and 1, 0 becomes a 1. The cool part with this is exactly the same as not P and U as well, P exclusive or U. Okay, so you need to start thinking about how these tables look and what the outputs are and how they map. The next one, same thing, we go 0, 1, 0, 1, 1, 0, 1, 1. Then we do not M, so we do 1, 1, 0, 0, because that's the opposite there. And then not F gives us 1, 0, 1, 0. And then when we join it together, there's only one case where they're both for 1s. So if we do not M and not F, the 1, 1 becomes a 1, 1, 0 becomes a 0, 0, 1 becomes a 0, and 0, 0 becomes a 0. Next one here, we've got WJ, not W, not W, or J. So again, we write the W's and J's as the inputs. So we go 0, 0, 0, 1, 1, 0, 1, 1. Not W becomes 1, 1, 0, 0. Not W or J. So if we look through here, we're looking anytime there's a 1 at all. So there's 1, so that becomes a 1. 1, 1 becomes a 1. 0, 0 has no 1s, so that's the unique case. So straight away that becomes a 0. And then 1, 0 becomes a 1. Hopefully you've picked up on how that all works now. So moving on, next one, have another go at those now that you've had a bit more of a practice. And then hopefully you've mastered the skills of and, or, not, and exclusive or, but using these new symbols. So the up arrow there means and, down arrow means or because there's more options. And then the little sniper crosshair thing means exclusive or. So just pause the video there and have a go. Awesome, welcome back. So we're going to go through the next bit in with this, okay? So to start up the top here, we've got 0, 0, 0, 1, 1, 0, 1, 1. So not D, right? We just invert it, so that becomes 1, 1, 0, 0. Not R becomes 1, 0, 1, 0. And then we've got the OR. So when we do that, it's widening it, so making more options out, okay? So then that means, see how when we did not D, there was only 2 options, and when we did not R, there was only 2 options that worked. When we merge them together, there actually becomes 3 options that are available in this circuit. So then that makes 1, 1, 0. So there's a 1, 1, there's a 1, there's a 1, and this is the key case over a 0. The next one, if we look here, we've got CU. So we go 0, 0, 0, 1, 1, 0, 1, 1. Not C, we invert those, so that becomes 1, 1, 0, 0. Not U becomes 1, 0, 1, 0. And then when we do not C, exclusive or with not U, we're looking for the times when there is only just 1, 1. So in this case, 1, 1, that doesn't work. This has got a 1, so therefore it's a 1. So 1, 0 becomes 1. 0, 1 becomes a 1 because there's only 1, 1. And 0, 0 becomes a 0 as well. Okay. Next one, we've got a KQ. So KQ, again, we go 0, 0, 0, 1, 1, 0, 1, 1. Not K, we flip it, so that becomes 1, 1, 0, 0. Then we go not K and Q, so then that's going to be funneling it up. So it's going to be focusing on something. And what happens with that? 0, 1 becomes 0, because there's not enough 1s. 1, 1 becomes 1. 0, 0 becomes 0, and 1, 0 becomes 0. So this is where we get some unique patterns. If we want it so that the input is only true when the Q is true, but K is a 1, or and then Q is, so when Q gets turned on but 1 isn't on, it still go. Okay, so see how this is a bit more complex, and the way this works is we do not K and Q will give us this output, which might be the particular output we need for the circuit we're trying to design. The next one, we've got MZ, not and then we're going to work out not M and not Z. Okay, so we're going to go through. So M is 0, 0, 1, 1. Then we got Z, we got 0, 1, 0, 1. And then not M, we flip the M's, so it becomes 1, 1, 0, 0. And then the Z becomes the flip, so we invert that, so it becomes 1, 0, 1, 0. And then at the end, not M and not Z, we're looking for AND, so that means it's joining together, or the unique case is only when they're all 1s, which happens in the first row. So 1, 1 becomes a 1, 1, 0 is 0, 0, 1 becomes a 0, and then 0, 0 is a 0. Okay. Right, so then we've also got the NOT versions of those three gates. So a NAND gate also looks like this. So we've got P, Q, right? Same as what we did before. So this is the unique case. When we do the NAND of that, basically we flip all these circuits. So zeros become ones and ones become zero. Sorry, that should be written a bit different. So let's just fix that up now. So it's the NOT, if we actually write that up all in brackets, which I assume I haven't done for the next one as well, which I haven't. So I'll just fix that now. And cool, right, so go back to this. Sorry about that. Fix. So not P and Q. So that becomes 1, 1, 0. So it becomes the NOT of everything, not just NOT of P. Okay, it's very important. Brackets do change the way that this structure works. So then when we do NOR statements, exactly the same pattern happens with that. So we've got PQ and then P or Q. Again, the unique case is the first row. So that's where it's a 0. And then if we do the NOT of P or Q, everything flips. So then it basically means that that becomes a 1 up the top there. So what you should see by now is that there's a whole heap of different ways that we can write this pattern, right? So because we saw that before, didn't we? When we did P and not Q, that also worked out to be that. And then there's these unique sort of relationships that you can build with this. And this is how circuits basically, you identify how they're redundant by looking at the actual inputs and then the outputs over here, and then trying to think about what's the better logical operations to make that work, okay? Which is what we're going to do with these. So these are the main ones that you should know. So you should know how to do A, B as the inputs, the NOT of A, the NOT of B, A and B, A or B, A exclusive or B, the NAND gate, so not A and B, and then the NOR gate, so not A or B. And then you should be able to understand and read why all of those sort of work. Cool, so have a go at completing this truth table. Okay, and there's something unique about this one, which we'll have a brief little chat about at the end. Awesome, welcome back. So basically we will go PQ and we'll fill in the blanks like we normally do. So we'll go 0, 0, 0, 1, 1, 0, and then 1, 1. So P or Q, oh sorry, and Q. So that's what that arrow means, we're anding. So P and Q, so this is not true, this is not true, this is not true, and then this is the unique case because we've got a 1 and then a 1, so that becomes a 1. Then if we do the NOT of this, we just invert it. So we get 1, 1, and then we get a 0 at the end. Then if we do exactly the same for this one down here, we'll go 0, 0, 0, 1, 1, 0, then 1, 1. So the NOT of P is when we flip all those, so that becomes 1, 1, 0, 0. The NOT of Q, we flip all those, so that becomes 1, 0, 1, 0. And then the NOT of P or the NOT of Q, we're looking for the, if there's at least just 1, 1 in either of these, it becomes true. So there is a 1, yep, there is a 1 there, there is a 1 there, and then here's the unique case where there is no 1, it's a 0 and a 0. Now, this is actually called De Morgan's law, because if we look at the last row here, the outputs are exactly the same, but the formula that we got there was different, okay? And this is the rule. So if you do the NOT of P and Q, so you P and Q first, then the NOT of it all, it's exactly the same as the NOT of P or the NOT of Q, okay? So this is actually known as a thing called De Morgan's law, okay? And this is a bit of a proof just to show you how it works. To formalize it, this is what it actually looks like. So if you have A union B, it would fill in all of this area here, wouldn't it? Right, so A union B would be all the yellow area, and then the NOT of that would be all of the blue area outside of it. If you then go A, NOT of A, so everything not A is everything outside of it, which would be including this crescent moon of the B. And then if you did the NOT of B, would be everything outside of this, including the crescent moon of the A. So therefore, when we union do the intersection of those two things, we get the same little blue area outside here. Okay, and then similarly for the opposite way of doing it. So instead of doing the union, you did the intersection or the OR gate, and that would work out the same with the Vesicle Pisces in the middle there. So true statements, if you do the NOT of A and B, It's logically equivalent, so it's totally congruent with the not of A intersection with the not of B. Okay, this is De Morgan's law, and it's a rule. Now, this isn't formally taught in the NESA course, but there's so many questions that if you understand this will make your life a whole heap easier. So A nor B is logically equivalent to the not of A and the not of B. So alternatively as well, if you do the not of A and B, so all of it not, it's equivalent to the not of A or the not of B. Okay, so A NAND B is logically equivalent to the not of A or the not of B. Okay, super useful. So you should know all of these. Have a go at this one. This might be a little bit more challenging. Okay, so just pause the video and have a go and see how you go with this one. Okay, welcome back. So we'll fill in the blanks. So we've got PQ, not of Q, P and not of Q, and then P and not Q or Q. Right, so for some reason, that's the input we're trying to check to see what happens. And we'll see what happens. Okay, so if we go here, we'll go normal, we'll go 0, 0, 0, 1, 1, 0, 1, 1. And then not of Q is where we flip all those. That becomes 1, 0, 1, 0. Right, like so. And then what happens here is we've got P and not Q. So we look at these two columns, the P and the not Q. And any time that we see a 1, 1, that is true. Everything else is false or 0. So there's a 0 and 1, so that's not both, so that makes a 0. There's a 0 and 0, so that just makes a 0. A 1, 1, so we found the unique case is 1. And then a 1, 0 leaves us with a 0. Cool. So now we've got this statement. So we've got the left-hand side inside the brackets. Now we have to all that with the Q. So over here we've got the Q. And we just fill it in. So anytime that there's just a 1, it becomes 1 overall. So 0, 0 becomes a 0. 1, 0 becomes a 1. 0, 1 becomes a 1. And then 1, 0 becomes a 1. Now, this is a pretty complex statement. Have a look at these outputs with 0, 1, 1, 1. And have a think, is there a way that you can make this simpler? Okay. And if you think about it, it's pretty much the same as the not of P and Q, isn't it? Yeah. So does everyone see that? So it's sorry, the P or Q, because it's the opposite way around. So you've just got to make sure that that P and Q up the top here gives you an output of 0, which is a little bit different, right? Because if we went through and finished that off, it would be the not of P and the not of Q merged together would give you that output. And it's a lot simpler than writing all that through there. So the other way, doing this next one, you got 0, 0, 0, 1, 1, 0, and then 1, 1. So the not of P is where you flip all that. So you get 1, 1, 0, 0. And then this one, you've got not Q, not P and or Q. So we just look at this, and if there's a 1, it's all good. If there's anytime there's all zeros, then it's not all good. So we get a 1, we got a 1, we got a 0, and then we've got a 1. Then we get to this last one here. So we're going to do all of everything that's inside here. So not P or Q, exclusive or with Q. So anytime that there's just a 1, it's all good. So there's just a 1 there. There's 2 1s here. So that becomes a 0. A 0 and 0 makes a 0. And then a 1, 1 makes a 1. So if we look at this again, the output is 1, 0, 0, 1. So a more efficient way of writing that, have a think, would probably be if we did P exclusive or Q and then the not of it all. Because we understand that that's, look, if we had 0, 1, 1, 0, 1, 1, 0 would be P exclusive or Q. But we're starting to see these patterns. So instead of writing all this out, this is what we call rambling, right? Which is where you just keep talking and writing more complex things that need to, than what's needed to be able to do it. Okay, so the rambler is where we look at an expression and there might be a simpler way of explaining it. Okay, so there's simple ways of explaining a chain of complex Boolean equations that means exactly the same thing. So if we look at that last example, we redo it. Can we make this more simpler? So we've got 0, 0, 1, 1. 0, 0, 0, 1, 1, 0, 1, 1, and we had these as our output, 1, 0, 0, 1. A more efficient way of doing it would be the not of P exclusive or Q. Do you see, instead of having to do, 1, 2, 3 options, we've now done it in 2 operations with 1, 0, 0, 1. And it's exactly the same thing. And this is what circuit designers get paid a lot of money for, where they're looking for these type of things. Probably not so now with our modern day circuits, but back in the day, that's what they used to do, is they would reduce these circuits down. So the original Atari with Steve Wozniak, that's what his job was to do, was to look at these circuits and try and work out more efficient ways of writing them, building the actual circuits. So make sure we always think about the simplest way of explaining it when we look at that last column. Okay, so the last challenge I want you to have a go is a little bit more. And what's going to happen with this, instead of 2 inputs, we're now going to have 3 inputs. So we're going to have P, Q, and R. So have a pause of the video there. My hint is count up to 8 for the input column and see what you can get. Awesome, thank you. Right, welcome back. So we've got P, Q, and R. So like I said, my hint with the first 3 columns is to write all the different combinations. And it's the same as if you count up to 7. So if you go 0, 1, 2, 3, 4, 5, 6, 7, all the way up to 8, and then not including 8, you'll find it. So the first 8 binary numbers is 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. And see how these first 2 in here looks exactly the same as the ones we did over and over, except now we've jammed zeros on the front. And then all we're going to do is copy this down here and then jam ones all on the front. So we're going to go 1, 0, 0, 1, 0, 1, 1, 1, 0, and then 1, 1, 1. The not of R is where we flip all these. So that becomes a 1, that becomes a 0, that becomes a 1, that becomes a 0, that becomes 1, 0, 1, 0. Cool. So now we've got all these different things so ultimately we're going to work out what this is. So P and R and the Q and not R. And we'll try and work out what this actually means. So P and R, we just read through the columns. So we've got P and R, and when we're ANDing, we're looking for a 1 in both of these. That's the unique case. So a 0 and 0 would make a 0. A 0 and 1 would also make a 0. A 0 and 0, again, a 0. A 0 and 1 makes a 0. So as soon as you do and they're all the inputs are 0, you're not going to get that across the line. Then this one, you've got a 1 and then a 0, which makes a 0. A 1, then a 1, which makes a 1. A 1, then a 0, which makes a 0. And then a 1 and a 1, which makes a 1. The next one, then, we've got Q or not R. So you got Q and then the not R. All you're looking for is any time that there's a 1. So in this case, we've got a 0 and then a 1, which makes a 1. A 0 and a 0, which makes a 0. A 1 and a 1, which makes a 1. A 1 and then a 0, which makes a 1. A 0 and a 1, which makes a 1. A 1, 0 and a 0 makes a 0. 1 and 1, which makes a 1. And then 1 and 0, which makes a 1. So that becomes a little bit broader. We then have P or not R. So we go P, not R, and we just go down the columns. So we've got 0 and a 1, which makes a 1. 0 and a 0 makes a 0. 0 and a 1 makes a 1. 0 and a 0 makes a 0. 1 and a 1 makes a 1. 1 and a 0 makes a 1. 1 and a 1 makes a 1. And then 1 and a 0 makes a 1. Cool. So we've done now the left-hand side. So the P and R, it's here. And then we've got Q or not R, which is here. So I just did that column there just to throw on and see if you could do it. But to get to this, you only need to do these 2. So now we're going to do the AND. So we're going to AND these 2. So 0 and 1 makes a 0. 0 and 0 makes a 0. 0 and 1 makes a 0. 0 and 1 makes a 0. 0 and 1 makes a 0. 1 and a 0 makes a 0. 0 and a 1 makes a 0. And then a 1 and a 1 makes a 1. Cool. Now, if you think about this, this is actually the ultimate conjunction, right? So if you, instead of doing all these complex things here, P and R, then and Q or not R, which gives you this output, it's exactly the same as if we did P and Q and R would give you this output. Okay. So instead of 1, 2, 3, 4 operations, you can do it in 2 with P and Q and R. That's what you should be thinking with these. Okay. So you should know all these by now. There's a bit of bookwork that I'd like for you to have a go. Just complete those worksheets 4.L.1 and 4L2, and then check your answers against them. And then, yeah, hopefully you've learned something with that. So hopefully you've picked up on how truth tables work. So you understand now what AND or conjunction means, or disjunction means. And then you've also got the exclusive or at the end, okay? And you should be able to write out these truth tables and understand them all back to front by now. Cool. So I hope you've enjoyed that. Thanks for watching. If you've enjoyed what you've seen, make sure you like and subscribe down the bottom. It really helps with the YouTube algorithm. See you next time on Steam and Steve. Adios.